Okay, hello everybody. Welcome back to another subtopic on biomechanics. This one is 14.3, lifting assessment methods. Now, I didn't have a better way to kind of name this subtopic, but know that this is the first of two subtopics that will talk about lifting assessment methods. I broke it up into two. I just didn't want to put 14.3 lifting assessment methods part one and point three would be confusing. So just know that when you're looking back at your notes during exam or whatever, remember there's also 14.4, which is going to include some of these lifting assessment methods. So I've basically taken these three, large, well-practiced sort of methods, and we'll talk about the first two here, and then the NIOSH lifting guide will be 14.4. So the very first method, what we'll talk about is actually, I love this one because this is a picture, you probably can't tell, but that's a Texas A&M University shirt. These are Texas A&M researchers in the ergonomics lab that was part of industrial engineering probably 30 years ago, 20 years ago. Yeah, probably 30. So in any case, this is the type of research that was done quite a bit historically at Texas A&M, probably still to some extent, or will be in the future. But anyway, this empirical test basically requires, some sort of machine or contraption that can vary, that can adjust the amount of weight that's part of some load that maybe has to be lifted, carried, or whatever. But basically, in a very controlled way, be able to manipulate and a load, in terms of the mass of that. They would use something we call a psychophysical method, and this is a formally defined method we call the method of adjustment. The essence of how it works is it's a subjective response, but you are performing physical work. So it's sort of the window between physical output and internal psychological experience. But you basically would be lifting things, say, make it a little bit heavier until I just barely can't accept it. And then do another operation where you start at it's too heavy for me. Oh, and now it's just barely, I guess, just barely not heavy to the point that I can acceptably lift it, do the work that I need to do. I'm using this term acceptable. I'm going to use it a few other times because that's that's the main question that goes with how much work can you do, how much can you lift? There is acceptable has kind of a broad range. But if you tell somebody, hey, if this was your job and you did this for 8 hours a day and you got paid this much, is it worth it for you? And at some point, add 1 more gram to the load I have to lift 100 times during the day, and no, it's no longer worth it for me. So, but this is about finding that acceptable point, because then when you can define that, look at it broadly across workers, you can modify your equipment, modify, the nature of the work being performed so that you keep everybody at a acceptable rate, or of course, more comfortable will be lower than the absolute acceptable. So yeah, the maximum acceptable weight of load, MAWL, adjust things until it's just barely too heavy and until it's just barely light enough to be acceptable as far as doing these jobs. Yeah, and so then generally, you do it several times, you average them out, and then you say, well, that's the absolute threshold. We don't want to be right on that line. Let's, adjust downward a little bit. Then that should be our design goal, or or how we strive to design an effective human, manual labor work system. All right, so that's maximum acceptable weight of load. That'd be one way where you could very precisely determine, what's an acceptable amount of work. Generally, it's a lot easier to say there's so many variables that go into whether or not this is acceptable, because just it being a certain weight doesn't take into account all of the different postures I might be in when I lift it, all of the number of times I need to lift it, and each of these can factor into like fatigue and injury risk. So we have basically, just like with anthropometry, we have a statistical way to express, acceptability. It is acceptable. So the percent acceptance of load, just like when we say, the 75th percentile anthropometric dimension, that means 75% of a population will fit at that, will have that length in that joint or in that limb or smaller. And so, yeah, so similarly, 75% of the population, if you say it's 75, that's actually the design goal, is usually the 75th acceptable percentile. That means 75% of people will be able to do it, are willing and able, basically. All right, good. And so now the Liberty Mutual tables, which is the second major method I want to cover in this subtopic. This illustrates that pretty well because there are a lot of aspects, that don't translate well to, a strict equation. But we know, obviously, when things get heavier, or if they're further away from us, or we have to lift them more often, each of these factor into, how acceptable a certain lift might be. So these tables, and I'm going to go through an example of how we use, break it down from a workplace description into, well, what is our weight limit? But one way you can use them is to say, okay, well, this value right here, 47, this is the male population percentages of acceptance for a lowering task. And so the way you can interpret this is 47% of males, I think this is because, just male population, lowering 69-pound load, if that's what we chose, or something around that, lowering it 10 inches, that's this spot here. Hands are 7 inches apart, and we're doing this every 15 seconds. That's how everything aligns, and we get that table value. That's how we would interpret this. So this is a good introduction to the Liberty Mutual tables method, because this is basically, Liberty Mutual is, yes, the insurance company. In 2022, they're represented by an emu. They'll probably be represented by some other animal, sometimes in the future, but they are a historically very active, insurance company, also involved in research, that feeds into, information about, well, is this a safe workplace environment? So they publish these tables and a digest that helps them, the lift. In fact, let me get to that, right? So Liberty Mutual tables, I put them in Canvas. You can download them and check them out for yourself. They include lifting limits, and these are all like, basically you can get to this level of, well, how many of my workers will be accepting of this sort of a task? Probably a more useful way to do it is the way that it is formatted in the digest. So there are some tables in the digest, and the description, it's a little easier to work with that, but the full absolute monster data set is also, I've included both of them. But it might be a little more, reasonable to say, let's just say I've got a normal workforce of men and women, and let's set the acceptability threshold at, if 75% of our female workers accept this workload, then we're good to go. And so then that's kind of I guess it's Liberty Mutual chose it, but it is kind of the standard to go to if you're going to say, let's design for a place with adult men and women. This is a reasonable threshold. And again, this is, remember that this is just acceptable. Doesn't mean they're going to love it. Doesn't mean it's easy. It's like, I can do it, I guess, and I'm willing to for the amount I'm being paid or for whatever other reason, right? Okay, so the tables look like this, and we're going to go through an example here of how to use them, because I'll probably want you to do a homework assignment / potentially final exam question on doing this. So make sure so I want to make sure we're clear on how to use them. Okay, so again, the Liberty Mutual tables, there are lift and lower tables, there are carry tables, there are pull tables and push tables. Each of these are different human biomechanical interactions. So they have different, guides, different limits that are, considered acceptable. And so first of all, for the lifting and lowering, and actually for all of these tables, they're going to specify where the lift occurs. This is going to matter because you can support more weight at your waist than you can above your head, or at least, with arms outstretched. Go back to 14.2 and review how, the moment about these biomechanical machines have, matter as well as the overall force, distribution. So yeah, so depending on where we're gripping or where we're moving to and from in lifting and lowering, we got to consider different tables. And so you'll see, our sweet spot, floor to knuckle, I guess that's where we can handle the largest loads, but they will give a range so that you can do your best to try to fit the current work task and find, lookup aspects in the table. But there's a lot of missing data in between. You may need to, do linear interpolation. In general, it's perfectly fine to just kind of, since we're estimating anyway, this is just a fudge factor thing. Okay, so this is kind of what I was mentioning. We would first say, okay, well, what's going on with this lift? Is it something, in this knuckle to shoulder range? Is it, I got to lift above my shoulder? Because they're going to be different tables we want to look at. Then we could say, all right, well, how far from, my belly or my torso to the center of the load, right? The center of mass or whatever. That matters. The further out we get, the harder it is to maintain that, that lift. Then what is the distance vertically? And again, we got 25, 51, and 76. Well, what happens if my, my distance is 45? Well, I would say you can either estimate or you can do linear interpolation. In any case, that's a reasonable engineer's, approach, and you can state your assumptions or whatever. But basically, this table is what it is, and then the frequency. And again, this is going to be one that's going to be, you won't be able to fit it exactly. But you can also see that, when we get down to these numbers, a lot of them don't change a whole lot between. So, if I'm in this category, it doesn't matter if I have 25 or 51 or anything in between. My acceptable weight limit here is 8 kilograms. By the way, these are, you'll notice these are in SI units, centimeters, metric units, and kilograms are the weights here. Okay, so here's our example. Squawk box. Back when TVs looked like that. So imagine now that, I don't know, somebody's carrying a gigantic widescreen that is something to handle. But in the manufacturing facility, let's say we've got, men and women that are lifting heavy TV chassis. I know they don't look like this anymore, but things, right? So, and they are, moving them from a conveyor. They come along on a conveyor, pick them up, put them on a stand. Then that stand, goes off to the next task. So let's define these lifts and look at it over the course of a day and see if we have an acceptable sort of situation here. Or actually what we should say is, well, what do we need to do material-wise in order for the mass of our TV chassis at Squawk Box, in order for that mass to be acceptable for the number of lifts and the nature of the lifts that we're talking about. All right, so if our conveyor brought us a chassis every 10 seconds, that is something we have to consider the frequency of our lifts. I'm doing a lift every 10 seconds. The conveyor is 3 feet off the floor. That's nice. That's a good spot for lifts. It's a nice ergonomic height as far as our ability to exert force. And the stand is 2 feet off the floor. So I'm doing a lowering action. That sometimes matters, but in this particular case, we're just lifting and lowering have the same limits. Sometimes it matters though in other methods. The stand is 2 feet off the floor. Yep. And oh, it's 90 degrees from my position. I have to turn 90 degrees. You maybe remember from earlier lectures that any sort of pivoting is problematic, especially if I'm, I'm maintaining a load here. We've got muscles in the back that will let us twist. They're not designed for also to twist and, you know, maintain a tense, you know, tense pattern of muscles across the torso in order to maintain a you know, a non-body load. Anyway, right. So this twisting could be a problem. We're going to look at it, you know, as we go with this example. All right. So here's our chassis, 18 inches wide. Oh yeah, huge future TV here. But let's say it's a box for some really cool thing. When TV doesn't work anymore. But 18 inches wide, 26 inches deep. Oh, let's say, okay, this is an antique TV manufacturer, so they do look like this, and they'll always look like this and be this big and heavy. All right, so no handholds, that matters for some methods. I don't know that it will for this, but the worker stands, you know, I'm 3 inches away from the conveyor and I'm 3 inches from the stand. So I've got a gap in front of me that in order to be safe and comfortable, that's going to be, you know, how I have to consider that 3-inch gap sometimes as far as the distance of my lift. Okay, so let's use the Liberty Mutual tables first. This is going to be pretty much a good first pass approximation. The next methods we'll talk about in 14.4 involve a lot more mathematical sorts of factors. So sometimes you can be off by a decimal point, and your final answer, you know, when you're multiplying 8 things, can sometimes, you know, lose, you know, there can be an error in there that sinks the whole thing. The Liberty Mutual tables are a great way to kind of see, am I in the right ballpark with this? Because it's an estimation sort of method. Okay, so let's do that here. Here's our guy. We know we're lifting and lowering. That is the big question here. Although we could be looking at carrying, we could be, but for now, let's do lifting and lowering. 3 feet off the floor to 2 feet off the floor. Let's call that in the knuckle to shoulder range. Okay, according to the stature of our workers, you know, our 50th percentile worker stature, you know, between 2 and 3 feet is going to classify as knuckle to shoulder here. But let's say we're going from 3 feet to 2 feet. That is a 12 inch or 30.5 centimeter vertical distance. So we need to keep that in mind. That's going to be something we have to use in our table. The size of our load here, the box, you know, the chassis, 18 inches wide, 26 inches deep. And we have to consider 26 inches deep. And we can assume, sometimes I forgot to put this assumption, if you can assume that the mass is uniformly distributed in this load, then the center of mass is halfway its depth, right? That's where we get 13 inches here. We started 26 inches, you know, to get my whole arm around it. I'm going to put it at 13 inches. You know, that's my balanced point. That's my center of mass. But that matters for how far out my arms are and the torque that this puts on my back, right? All right, 3 inches is additionally the gap that I got to reach over, remember? So we're going to go 16 inches, and then we're going to convert that to metric, and it's 41 centimeters. We also know these guys are arriving one every 10 minutes, or sorry, 1 every 10 seconds, So I don't have 1 in 10, but I've got 1 in 9, I've got 1 in 14. And so again, I estimate, say it's pretty close to 1 in 9 seconds. Or I could do linear interpolation, but again, a lot of these table values don't change a whole lot. And so, you know, at those fine details, so it's okay to approximate or at least round conservatively, right? So make it, you know, for each of these, I would round it to be the more extreme, you know, the harder aspect on the human. So I'd go with the 1 in 9 rather than 1 in 14, because I'd want to make sure that it was safe enough for them. And if they can lift it every 9 seconds, then every 10 seconds should be a little bit better on them, right? All right, so anyway, that's what we're doing with this table here. So we've got our lift and lower tables. First of all, 2.6 is lifting and lowering. I've identified it's a knuckle to shoulder range here. We know it's 41 centimeters from our body to the center of the load, to where the load acts. So, well, I've got 38 centimeters. That's pretty close. I'm going to go with that. Okay. Any of these other ones are shorter distances. So yeah, I'm going to go with the largest one there. 30.5 centimeters. So, okay, well, it's somewhere between these two. Again, I'm not seeing a ton of difference between the two in these columns. So I'm going to assume it's not too big of a deal to. Well, I'll look and see if I need to basically make a distinction or do linear interpolation. 1 in 10 frequency, again, I'm going to use 1 in 9 because that's the closest in the table here. And I look everything up and I say, okay, well, it's 8 kilograms, whether it's 25 or 51. So the 30.5 being between them, we know 8 kilograms is a pretty good estimate. I could use linear interpolation. In this case, I would guess that it won't change much, from that estimate of 8. Okay. So there are other tables. Make sure you're using the right table based on the right sort of human work activity. So we have the carrying tables, right? And you use them very similarly. There are ranges of, how far you're carrying something, what is the load, where are the arms. It matters if you're carrying with straight arms, straight down versus bent, because of, we have different force allowances, basically acceptabilities based on that. Yeah, so here with straight elbows, I can handle, I guess, a little bit more on the front end, but 21 to 11 kilo, I don't know how that happened. Anyway, okay, anyway, look in the tables to make sure, I don't know if this is exactly right or if I miss something, but in any case, there you go. So there's those tables. There are push and pull tables that look at where are the hands for this push or pull activity. Those matter, the distances, and are you just trying to shove something to get it going, then to overcome static friction, or is this a continued sort of exertion? Those those are two different types of activities potentially. All right, there we go, folks. That's 14.3. Tune in for the NIOSH lifting equation in 14.4.